And you did yours in C++?
No, mine's Python.
Okay. Good. All right.
I'll get to this with taking, not time steps, but steps in radius or pressure.
Yeah.
Just as fast or as C++. So it's not like I'm
no, that part.
gaining anything from
that part is
stuff at NumPy.
Instantaneous. You know, it's not that fast, not that slow.
The 2D interpolator, I won't even need the 2D interpolator for loading the table anymore, but it runs slower than kind of doing two 1D ones, but you only do it once. It wasn't too bad.
Boy. Not very visible. I'll turn down the lights. Hi.
Hi, is there a sheet of paper up there?
There is.
Yeah. I'm gonna need that for a final.
All right. Yeah, don't lose that.
Thank you very much.
Welcome. Where's everybody else at on playing around with the TOV solver?
He's got another one.
Mine's low ball on
Check your units.
it. Should be CGS, but we'll see.
Okay.
Yeah, I did it the easy way and just did everything in CGS. Not very relativist of me.
Actually, that was one thing I did get done. I finally got around to finishing like the generic constant / units class that more or less can automatically do most things.
Share.
It's ugly. I got to clean it up a little bit, but you tell it's like, okay, well, this is CGS, and I want everything in geometric. Pass in that instance of it to wherever your objects are.
Yeah.
Now, once I clean up the really ugly DOS to it, put that on a package or something.
Yeah. That'd be helpful, I think, to everyone. But also, like, if we just made pressure as a function of density plots, tables for each equation state.
Yeah.
Because the point is to solve the TOV equations.
Yeah. That's the easy.
That is the easy part. I mean, once you've done it for the polytropic equation state, you're essentially done if you have pressure as a function of density.
Yeah. Switching to an adaptive step or an adaptive solver, right? Yeah. Eliminates some of the problems with having to like look for the where it's crossing 0.
Did you use a built-in function for that?
No, the adaptive solver I had last semester in Brian's class. He was teaching the real one, so modified that slightly. Because with that one, like before, if I was solving it, everything's a function of radius. I was doing something stupid, like I had that 1 minus 2m or 2m over r.
Yeah.
I had that as a square root of that there, so it would just blow up at that point.
Yeah.
Taking where I only take the square root when I'm solving for like the baryonic mass, which technically I don't even need really.
Yeah, I haven't even solved for the baryonic mass.
Yeah, I've got that in the times one there. But before it's like I had to like explicitly catch the exception on the invalid floating point operations, and just the times or the radial step. But with the adaptive solver, it just I set it so it just increasingly gets closer to whatever the
How does it choose the adaptive step based on like pressure scale height or something?
So the adaptive step is it just tries going plus dr and then plus half dr plus half dr. And then,
Zeno's paradox.
Yeah. Either increasing dr or decreasing it by some background.
Yeah.
I've got to work that somewhere. So
yeah.
Now, if you switch it around and have everything as derivatives of pressure instead of radius, then you can just tell the delta P equals 0. You don't have a problem, but even with the adaptive solver, it still takes a lot longer to solve it because it changes.
Yeah.
I'll show you what I did. I over-engineered mine just for fun.
Yeah, mine is definitely not as simple as.
I think Joe, you will be here. We're running a little late, but I think Kyle can't make it today. So this might be we break few for the day. I thought I finally got down and wrote my TOV solver. So I thought I'd show you guys what I did as you're working on yours. Now, I mean, I think if I sat down and wrote this again, it wouldn't be the same code. And if I did that 10 times in a row, I'd end up with 10 different codes. So there's like a million ways that you could do something which seems very simple. But I'll show you what I did and just some gotchas. There we go. Is that better? For doing this. So the main thing, you know, you remember from the TOV equations. Let's see if I've got them up somewhere. Maybe. No. But from the notes, the main thing, I mean, it's just a system of first order ODEs, right? And so in that respect, it's pretty trivial. And all you got to do is define your right-hand sides and then feed it to a proper ODE integrator. I do recommend that you just use a built-in integrator like from SciPy or NumPy if you're using Python. You can, ODE. Yeah, for instance, that one will do a fine job. I think the default is RK4 for ODE int. I did something different because I had an adaptive integrator lying around that I just forced into service for this.
Problem with ODE in this problem, you have to specify all your points that you want to calculate the equation at. And if you don't know what that maximum radius is, that's where the pressure drops to 0.
Yeah.
And it's a little harder to work around.
Yeah. The stopping conditions are the trickiest part for this, right? Because if you're integrating forward, right, the general process for integrating the TOV equations is start from some central density, just specify some central density, and then you shoot forward in radius, solving the right-hand sides as you integrate forward in radius. And then you got to choose where to stop. Best place to stop is where pressure goes to 0, right? That's the edge of the star. You're outside the star. And so most of my code is looking for the stop, where to stop. So let me just show you what I did for mine. So the main execution of the code starts here, where I specify some central density row C, and then I set up a bunch of stuff. The way that I did my arrays in NumPy, so everything's a NumPy array here. These are just one-dimensional array, or arrays of length 1 right now, and then I just append new values onto the end of the array as we go. Initially, since the derivatives, the right-hand sides blow up at the origin, I just specified some small step size and then integrated the mass analytically there and assumed that the pressure was constant. That's one way you could do this. It's perfectly fine, it's perfectly accurate. Another way that I've done it before for equations like this is to actually do a Taylor expansion about r equals 0. That would be accurate, but probably overkill. So that's the initial conditions then. And then from this point, this rad plus dr, some very small number, which is my absolute tolerance here, we start integrating forward. And so I've defined a few EOS routines. EOS, density from pressure, which inverts the equation of state to give you density from pressure. Energy from density, and those routines are up here. And they're just the polytropic ones that we specified, right? That's all they are, just right from the notes. This commented out stuff, code's a little messy right now, but that's for the table-based equation of state. That gets harder. Okay, so having set my initial conditions, I compute the derivatives for that first location and then start integrating forward. The way that I have done it, I haven't used ODEInt, I wrote my own ODE integrator. And it's, like I said, over-engineered. So it does something called adaptive step size control, where it uses run-to-kata formulas that have embedded low-order formulas. and then it compares the errors between the high order and the low order to adaptively choose your step size. And so basically, instead of specifying the number of points along which I'm going to solve this thing, I specify the error that I want the ODE integrator to maintain during the steps by comparing the low order and the high order solutions. You can find this in numerical recipes. And I was turned on to this by Saul Tucholsky himself when he had an office next to mine at Caltech. And he once told me that if I wasn't using one of these adaptive step size control integrators, I was being criminally negligent with US taxpayer dollars and computer time. I was like, okay, Saul. Turns out they don't really work for our complex simulations. I tried it. But they work great for simple ODEs like this. And so this is the main loop then. And I'm just looping over until I find that 0 point for the pressure. And I'll show you how I do that. This is the multi-stage Runge-Kutta. The way that I have written it here, it looks very much like the equations that you would find on Wikipedia. Okay, so I'm just looping over the number of stages in my Runge-Kutta solver, which for RK4 would be 4, and then summing up these various coefficients based on the calculation of the right-hand sides, K and L, right? So that's all that we're doing in each one of these stages. And I'm storing the right-hand sides, K and L, as I integrate through the various stages. And then in the final update, these just get summed with the appropriate Runge-Kutta coefficients from the Butcher tableau. Does everyone know what I'm talking about there? If you're using ODE, you really don't even have to know. But if you look at the notes that I passed out for the TOV problem, right, the different Runge-Kutta solvers have different coefficients for these different parts of the integration. And you can express this generally as Butcher tableaus. And that's what I've done here. And so for this, actually, and here's the over-engineered part, I can arbitrarily choose any set of Runge-Kutta from second order to fourth order, third, fifth, whatever I want. I have a bunch of Butcher tableaus in here for various different kinds of Runge-Kutta integrators. And almost all of them have embedded low order solutions. Took me a while to type this in.
General recipe for the nth order?
No. There are many and varied ways to determine what the optimal coefficients for an nth order Runge-Kutta are. And it depends on what your requirements are. If you want strong stability or not, if you want to minimize the number of stages, if you want to maximize the actual order of convergence, no. Up to about third or fourth order, you might have some theorems about optimality of Runge-Kutta coefficients, but beyond that, it gets actually quite complex. So actually, what's the highest one I have in here? Oh, here we go. This is a great one. So this is an 8th order Runge-Kutta. Look at the coefficients on this guy. Think about how many times it took me to type these in correctly. And it still doesn't work very well. So you don't have to do that, right?
Template C++ won't slow that.
And automatically generate the coefficients?
It's in yeah, it's part of Skynet.
Okay.
So,
there are formula for generating the coefficients for Runge-Kutta integrators. You're not guaranteed to
I'm not
get
sure what order it actually works up to.
Right. Right.
Probably, I think it's at least up to 6.
Suffice to say, almost all this part and all the code I just showed you can be done by ODE int if you just use the Python code. But I already had this, and so I went ahead and used it. And so literally most of the main loop is finding where to stop. And so in my code, what I've done is to specify an absolute tolerance, which is just some small number. You know, like I think I put 10 to the minus 10, like a very small number numerically speaking. And if the pressure goes negative, what I do then is something that Steve was just talking about. I bisection. I play Zeno's paradox, where I retake the step with a step size dr, which is half the size of what I used before. All right, because if it's gone negative, that means I've overshot. And so I'm going to go back, and I'm going to take half the step size until I get close to 0. And for me, close to 0 is a step size that's less than my absolute tolerance. And then I'm done. And that's it. So if neither of these two things are true, I'm not done and I haven't overshot, then I recompute my next time. I continue on to do the next time step. You don't have to do this. But one of the things about these embedded Runge-Kutta methods is that you can use a low-order solution to make a very good estimate of the truncation error of your method, right? I mean, all of these integrators, whatever order, when we talk about order, we're talking about the truncation error, right? Everything's a Taylor series in physics, everything, including Runge-Kutta formula. And so you have to truncate that series at some point, and that's what we talk about when we mean order. And so by comparing the orders of accuracy of two different versions of the Runge-Kutta, I can directly empirically measure my truncation error that I'm making, and then take a step size that is maximally big to maintain some error level. It's very slick. And so for some of these integrators, you know, I can solve an entire star in 50 points to 10 to the minus 10 accuracy because of the high order solvers. All right. Now, this is what you could do instead. So if you didn't have this embedded method, you could take some step size, which is based on the local gradients, the scale height, basically. That's what I would do. Like, you've got dPdr from your right-hand sides, right? And so you would take your pressure, divide by dPdr, you've got dr, and take some fraction of that to be safe. And then on we go. And if I open a file and I spit out to the file the various things about the solution. That's the main loop. That's it. Okay. So the magic sauce is in the ODE integration, but then also specifying your right-hand sides correctly, which I've got up here, which are just directly from the notes, and then deciding where to stop this thing when has pressure crossed 0. And how you feed information into this thing, how you vary the central density, et cetera, is completely a choice up to you. But the point for this first polytropic equation of state is to figure out mass versus radius, basically, for the mass of the star as a function of central density. Equivalently, those are the same thing. So for my version of the polytrope, yeah, here we go. So this is what I get. And this is a very weird curve. Okay, so this is a gamma equals 2.75 polytrope with the adiabatic index, or adiabatic constant that I gave you. And so as the mass of the star increases, the radius goes from itty bitty out to 14 kilometers and back to itty bitty, right? Back to 9 kilometers or so like this. That's a really weird curve, and it's not one that you would expect for a normal, realistic neutron star equation of state. But it's because gamma is constant. That's why this happens, right? If you take a real neutron star, the adiabatic index gamma is not constant through the star. It's maybe 2.75 at the center of the star. And so this is an extremely stiff equation of state, as we would say. More realistic plots, and I don't have one from my solver just yet, would look something like this. So same thing, mass versus radius, but they don't do this. Low mass neutron stars have very large radii, which we would expect because they're degenerate, right? Degenerate equation of state, more massive makes them smaller. And so they come in, go up, and then peak. And so the maximum mass where that turns over is reflective of general relativistic instability starting to set in. Whereas you have a double value there, basically. So massive neutron stars up here, you know, it's double value. And what that actually means is that you can't have a neutron star more massive than that. And so, yeah, so for this equation of state, you know, my maximum mass is somewhere here, almost 2.5, something like that. What was the exact number, Steve? 2.41, something like that?
Yes, 2.4 something. And the radius, 12.5, 12.6.
And this is the run of density as a function of radius. No labels on this plot, but this is for the polytropic equation state. So that's it.
What is the radius in on the graph?
Oh, down here, I think it was in centimeters.
Oh.
Up there, it's in kilometers. Yeah, and so this is the other thing. You have a choice about what units. And in mine, I used CGS everywhere, just to keep it simple. Just to keep it simple. But you could use geometrized units, or you could use relativistic units where the solar mass is also equal to 1. And the conversion factors are in that table in the notes. Questions about that?
Do you have your table lookup?
So I was starting to work on that, and there's a couple ways you can do it. Now, I'd actually be satisfied if you did the following. It's not quite an ill-posed problem, but you've got to make a choice about what the electron fraction is in the star. And you also have to make a choice about what the temperature is. And so these tables that you're going to use, they are 3-dimensional tables with abscissa, density, temperature, electron fraction. And then all the various things are interpolated from those 3 abscissa. So when you're doing this, solving the TOV equations, we care about cold neutron stars. 1. So temperature, set it to the minimum. It's a cold neutron star. But now, YE is still a free choice. And I wouldn't fault you if you just said YE equal to the minimum. You will get a mass and radius relationship that will not be quite right. The reason is that cold neutron stars don't have YE equal to very small number. In other words, neutron stars aren't all neutrons. Neutron stars are actually in beta equilibrium, meaning that the rate of electron captures is balanced by the rate of beta decays. And so if you solve that rate equation, you actually get a YE profile that is not constant, right? And it depends on the density, where that beta equilibrium value for the YE is. And so the right way to do it is to actually solve for beta equilibrium. And I've done that. I don't have any good plots. It involves some root finding and a lot of hacking on the equation of state. And so you can do it the easy way. I think what I'm also going to do is just post some pressure as a function of density tables for each of these things, because at the end of the day, that's what you end up with. When you solve for beta equilibrium for one of these equations of state and you pick a cold temperature, all you end up with is breaking that degeneracy with YE, and you divide out YE as an independent variable, right? YE becomes dependent on the pressure. And so then you just end up with a monotonic function between pressure and density that you can use to interpolate between, to invert your equation of state to solve the TOV equations. And that's what I've done in here. I will show you what I mean by this. So beta equilibrium means chemical potential of the neutrons minus chemical potential of the protons minus chemical potential of the electrons is equal to 0. That's what it means. Now, conveniently, in the table are these chemical potentials as a function of density, temperature, and YE. And so you can get those right from the table, and you can solve this equation. You can root find this equation for the appropriate electron fraction YE for the pressure that you've specified, right? But that involves a couple steps, because if you just come in with pressure, you've got to solve for density, solve for YE at the same time. So it's a multi-dimensional root find. I think there are SciPy things that will do this for you. I did it by hand. Well, I used some SciPy stuff, but I didn't use the multi-D interpolator. And so once you do that, you can actually specify, let's see here. So that's what this is. Oops, come back. Okay, so for each, I specify some table of pressures. This is equally spaced in log. And then I find the density that corresponds to that pressure at beta equilibrium. And so my routines for doing that, find rho, is up here. So find rho does a bisection solve on find pressure, where I've got some pressure that I want, and then some interpolated pressure as a function of some YE and the density that I'm specifying. And then this find YE is a bisection which solves beta equilibrium for some specified density, and that's up here. And so this is just turtles all the way down to do these bisection solves. And so I wrote it in the most naive way, and this is super duper slow. Do better than this. But I just whipped it together. And it works, and it solves, but it is super duper slow because of all of these nested bisection solves. It's very expensive.
There's one value you can load from the table that you don't have to do those on.
Which value is that?
Union.
Oh yeah, that's right.
That's
right.
You can just load that and then do a NP sign,
Yeah.
NP diff, and look for the only one that's not zero.
Yeah,
That's where it crosses between those.
that's right. That's right.
A lot faster.
It is a lot faster. So mu is the chemical potential of the neutrinos. All right, that would work. So you could do this, or you could just set, I'm fine with you setting YE equal to a constant value at the minimum. That's not quite right. But I'll also post some pressure as a function of rho tables for you to use. Because the main point here is to solve the TOV equations with these general equations of state. And in beta equilibrium for a cold neutron star, it just reduces to density as a function of pressure, pressure as a function of density, just like the polytropic equations say, but it's not analytic anymore.
Don't forget the energy shift too if you're loading from the tables.
Yeah.
It's not always zero on all of them.
That's a good point. That's a good point. So some of these tables, most of these tables are offset in their energy. So the internal energy in the table includes binding energy of the nuclei, and that's negative. And so the energy can actually be physically negative, the internal energy, because it includes the binding energy of the nuclei. And so we store everything in the tables in log. And so in order to make that work, we shift everything up by a constant value and then take the log. And so the energy shift is stored in these tables. I still have my Python notebook up. Oops. So that's in the table. So here's the list of keys. Most of these tables have something called energy shift, which is that shift value, non-logarithmic shift value.
So we add the log of that one to the,
Don't do it in log space. Do it in linear space. Yep. Yep.
Or, yeah.
That's right. But after you do stuff with the table, because the table is all in log and all includes this energy shift in the energies. Okay. And other questions?
The energy density when you're converting units.
Yeah.
So the same units as your pressure.
Yeah.
Geometric units.
Yeah.
On that.
And well, the table is all stored in, well, it's almost all stored in CGS. The temperature is not. The temperature is in MEV. Entropy is kV per baryon. Yeah. Other questions? Feel free to ask on the Slack channel as well as you're working on this. The polytropic part should be very straightforward. And once you've solved the polytropic part correctly, you've got a working TOV solver. It's just substituting in a different equation of state, just a different relationship between pressure and density. Everything else about the TOV solver is the same. But I was playing around with this morning, so I thought I would show you. Okay. Ready to get to it? Yeah? All right. System off. Okay. Hey, look. I almost don't have to rewrite the constraint equations, which is what I was going to do. Well, the problem is look at how bad that eraser is. This eraser is black. Okay. Okie dokie. So last time we derived the constraint equations for the 3+1 decomposition of Einstein's equations. And we used the Gauss equation contracted twice, Kodotzi equation contracted twice, and that gave us constraints. Those constraints are very analogous to the constraints that we have in electromagnetic theory, but now we're dealing with GR. We have one more equation, purely geometric equation, that we didn't use, and that was the Ricci equation, which gives us a relationship between, well, it gives us the expression for the Lie derivative of the extrinsic curvature. So now that we've got these constraint equations, let me write up the constraint equations that we solved. So I'm just going to leave them over here. The Hamiltonian constraint. That gives us our mean, the scalar, plus the mean curvature, minus the extrinsic curvature, contracted on both indices, is equal to 16 pi rho. That's the energy density, and that's the Hamiltonian constraint. Right? This is one equation. The momentum constraint is a vector equation. Spatial derivative of kBA minus spatial derivative A of the scalar is equal to 8 pi SA, where SA is our momentum vector. Question?
Should it be a B on the first B?
Yes. Of course it must be. Thank you. All right, so there's our constraints. All right, let's talk evolution. Okay, so let's start with our definition for the extrinsic curvature, which is -1/2 Lie derivative along the normal vector of our spatial metric, gamma AB. And then recall we're going to use the Ricci equation, which we derived last time. And remember those, well, 2 times ago? Purely geometric relationship. No physics involved, but incorporating this with the Einstein field equations brings us in contact with physics. And so the Ricci equation was the Lie derivative of the extrinsic curvature is equal to normal vector ND, normal vector NC, gamma AQ, gamma BR, 4-dimensional Riemann curvature tensor DRCQ, minus 1 over the laps of the spatial derivatives, second spatial derivative of the laps, minus KCB, KAC, the extrinsic curvature. Okay, so that's the Ricci equation. Right? Remember, this Lie derivative is like a time derivative, and it's like a directional derivative, and it's like that because we're taking the Lie derivative along the normal vector, which is purely time-like. And so in that sense, it's like a time derivative. All right. But the Lie derivative is not really a perfect time derivative. It's not quite natural. And that's because NA, the normal vector, is not dual to our surface, omega A, that surface vector. All right? In other words, NA, this person, the omega A, which is equal to minus alpha, the laps, 4 metric inverse, gradient of T, which is equal to -1 by the normalization, right? That's the normalization that we have for the normal vector, right? But this is not equal to 1, right? Which it would have to be if these two things were dual of each other. And so the Lie derivative along this normal vector is not exactly a time derivative. In order to solve for the evolution equations for how the gravitational field is going to evolve, we need to turn this into something that's much more like a time derivative so that we can use it in that way. And so we need to come up with some vector that's not the normal vector, which is dual to omega A. All right, so let's just define the following. TA, which is going to be equal to the lapse times the normal vector plus beta A, where we are introducing this beta A, and I'm going to call that the spatial shift vector. So it's purely spatial, and it gives us this shift in coordinates. And I'm going to draw a picture. I'm going to try to draw a picture, which perhaps will illustrate what I mean by that. Let me write a few more things. So this new definition, TA will be dual to omega A. So in other words, TA omega A is going to be equal to alpha NA omega A plus BA omega A equals 1. By construction, right? And so we have added this shift vector so that we come up with a new vector based on the normal vector that is now dual to omega A, which will allow us to transform our Lie derivatives into something much more like a time derivative for convenience. And beta A measures the amount shift that the spatial coordinates shift within a slice with respect to the normal vector. Put this in quotes because that's the name of the vector. Shift within sigma, our spatial slice, with respect to the normal vector in A. Okay? I think it's much easier. I know I'm going to need that again, so I'm going to try not to erase it. Let's draw a picture. Where's blue? Well, let's draw a picture. Maybe I'll draw it up here. Okay, so let's take a couple of neighboring spatial slices sigma. There's one. There's another. This is going to be at time t. This is going to be at time t plus dt. That's not the vector time, that is the scalar coordinate time in this 4D space-time. And each one of these is my embedded hypersurface sigma, right? Purely spatial hypersurface sigma. Here, to illustrate what beta is, I'm going to specify some location, some event, which exists on this hypersurface with spatial coordinates xi, label it A, some event. And I'm going to take the normal vector up to here, some vector normal to that hypersurface, in between these two adjacent hypersurfaces. And that distance there is going to be the lapse times the normal vector times dt. Remember, we said that the lapse is essentially how quickly time is evolving in between the slices, right? And so the length of this vector, alpha times the normal vector times dt, right? Alpha, the lapse is like a rate, the velocity of time change. Okay. And so now, if I've got up here in this hypersurface some other event, call it B, the distance between this event, which we'll call A prime, and B, that's going to be dxi, my coordinate change, plus beta I dt. So this is telling me how my coordinates are shifting as I evolve forward in time. Okay? Now the full time difference, the full invariant interval between these two things, we could just call dxa, where again, now I'm using A to represent that that's a 4-dimensional interval versus my 3-dimensional interval dxi with shift vector beta I. where I wish I'd written bigger. All right? And so to see this, this length of time here, something like that, we've got dxi is that distance there, right? So that's the distance without the shift vector, which would give us the wrong thing. So what's the point here? The point of introducing this shift vector, maybe I'm losing the forest for the trees a little bit, is so that I can have the same set of coordinates between, the same set of spatial coordinates between neighboring hypersurfaces. In other words, if I've got some event in this hypersurface that's at rest, and so it's just following a geodesic world line through time, right? It's not actually moving. I want its spatial coordinates to be the same in the next hyperslice, right? In the next hypersurface, in this foliation of spacetime. I don't want there to be any sort of just evolution of the spatial coordinates. I want time to evolve. I want the time coordinate to evolve. But if it's at rest, and just following a geodesic world line, I don't want its spatial coordinates to evolve. And that's what the shift vector does here. That's what the shift vector does, is allow that to happen. And so I can define and separate my coordinates between space and time much easier. Okay. Right. And I already said that. Okay, so along with this beta, which measures the shift in my spatial coordinates, I just said this in words, but alpha measures rate of proper time. Right, so these two things together tell me how the coordinates evolve, right? So the lapse and the shift vector tell me how my 4D coordinates evolve in this 3+1 separation of gravity. Right? And so these are two important concepts, which makes 3+1 okay. In other words, when we finally choose a basis, alpha and beta are going to represent my gauge conditions. When I finally specify a gauge, that's going to be represented in the form that the lapse and the shift vector take. And I'm going to show an example of that later with the Schwarzschild metric, of course, with the Schwarzschild metric. Okay, so another property of my vector time is that it has the duality relationship. I'm going to write this right here because I don't want to erase some things. It's dual to its spatial gradient, like that. Where this is the coordinate time t, right? The scalar time t, okay? And what that implies then is that you'll see why I'm not erasing this. I'm going to need the Ricci equation in a second. And it takes an entire board to write, so I don't want to write it again. So this duality implies that all vectors, okay, such that TA dt, and for that matter, alpha lapse times the normal vector dt, that start on one slice on, let's call it slice 0. We'll call it slice 0. Or better yet, I'll call it slice t for some time, scalar time coordinate t, will end on the same slice at some time t plus dt. Can you read that? T plus dt. Okay? That's an important distinction, because if I didn't have well-posed coordinates for my foliation of space-time, I could imagine two vectors which start purely spatial, right, in this hypersurface at time t. And as I evolve forward in time, they would no longer exist purely in the same hypersurface. There could be some, they get out of whack from each other. That would be bad. That would be challenging. That would be difficult. That would be not what we want. And so the relationship, the definition of this vector time and its requirement to be dual to the gradient of the proper time, coordinate time, ensures that this is the case, which is a desirable property for evolving, okay? And also, the Lie derivative of any spatial tensor, is purely spatial. Which is handy, okay? So if I've got some geometric object, a tensor, that is purely spatial, and I take its Lie derivative, that Lie derivative is also purely spatial. So for example, for the projection operator, if I were to take the Lie derivative along alpha NA, the lapse times the normal vector, of the projection tensor, that'd be 0, right? Okay. It's funny, it's only this board that gets so gunked up. Okay, so now, let's use this new vector time, the lapse and the shift, and the Ricci equation to get to some evolution equation for our metric quantities and extrinsic curvature. All right, so let's consider the Lie derivative along this new time vector of the extrinsic curvature. So now this is starting to look like this, but now instead of the normal vector, I'm using this new time vector. All right, that's going to be equal to the Lie derivative along alpha n plus beta of KAB, right? That's just the definition that we had for the time vector. And that's going to be equal to, just by the differentiation rules of the Lie derivative, alpha times the Lie derivative along the normal vector of the extrinsic curvature plus the Lie derivative along the shift vector of the extrinsic curvature. Okay? So now we can use the Ricci equation to get rid of this right here. Okay? So we can substitute right into there. Okay? And then before we do that, let's rewrite this projection, right? Remember, this is a projection of the 4D Riemann tensor with two components in the normal direction, right? That's what this thing represents. So let's rewrite this projection operator first and get into a form that's going to be more useful to us. Save that for later. Okay, so normal vector ND, normal vector NC, gamma A Q, writing a little small. Can you guys there see that still? These are big equations. Gamma vector B R, 4D Riemann tensor, dr C Q. That's going to be equal to projection inverse spatial metric, gamma CD, gamma AQ projection operator, gamma BR, 4-dimensional Riemann tensor, drCQ, minus gamma AQ, gamma BR of the 4D Ricci tensor, RQ. Just working that out. Okay. Now we can use Gauss's equation, which I didn't write up, but we used that last time to derive the Hamiltonian constraint. Gauss's double contraction of the Gauss equation gave us the Hamiltonian constraint. So we can use that to actually rewrite this first term, right? This actually comes from the Gauss equation. All right. And then we can reuse the Einstein field equations to substitute this second term. Okay? So, doing that, so I'll write this up. Gauss equation plus Einstein field equations gives us the following for this projection operator. That's going to be ND, NC, gamma AQ, gamma BR, projection of the 4D Riemann tensor DRCQ is going to be equal to RAB, the Ricci tensor. Again, that's now the 3D Ricci tensor, dropping this 4, plus the scalar extrinsic curvature minus KAC, the extrinsic curvature, KCB, minus 8 pi gamma AQ, gamma BR times TRQ minus 1/2, right, GRQ, the metric, times T, the trace of the stress energy tensor. Okay, right? Let me just write that out explicitly, where T is defined to be the trace of the stress energy tensor, TAB, GAB, the 4 metric. And again, you know, this term came from the Einstein equations, right? And now it involves physics. So we took this projection operator. Our stress energy tensor is what represents physics and what's going on in the geometry of the space-time. Okay. I should have written this like at the top of the board. This thing is going to be jumping over it for a little while until we finally get rid of it. Okay. So last little thing, let's make one more definition, which is the spatial stress.
It's just a small thing.
Right.
With the last K, it's upper C, should it be lower B?
Yes, it is. Thank you. Okay, the spatial stress we're going to define as following. SAB defined to be the way that you would expect. Gamma AQ, gamma BR, that's a projection. Oops. I use different indices, gamma C, gamma D, of TCD, doesn't really matter. So that's our spatial stress, right? Just projecting the full stress energy tensor into our spatial hypersurface. And then the trace of that, SA, the scalar. All right, so now with those definitions, with this re-expression for the projection operator in the Ricci equation, let's put all this together. Using that, therefore, we have gamma AQ, gamma BR times GRQ times GEF of the trace of the stress energy tensor. We can re-express that as gamma AB, the spatial metric, all times gamma EF, inverse spatial metric, minus NENF. That's from the definition of the 4D metric. TEF. And then finally, that's going to be equal to gamma AB all times S minus rho. So this scalar stress and then the energy density, right? That's coming just from the definition of those two quantities. So I can simplify this term quite a bit by doing that. So now, I think we're good with all this. Yeah? Let's write our line derivative again. So, line derivative along my time vector of the extrinsic curvature, KAB, now is going to be equal to minus the second spatial derivative of the lapse plus the lapse times RAB, the Ricci tensor, minus 2 times curvature scalar, or the extrinsic curvature KAC, KCV, plus KAB, close parentheses, minus 8 pi, here comes physics, alpha SAB minus 1/2 gamma AB, the spatial metric, all times capital S minus rho, and then plus the lie derivative. My notes got cut off a little bit. That's got to be along beta, right? Lie derivative along beta of KAB. And I haven't done anything with that last term yet. I've re-expressed the first term in the lie derivative. Okay. And we're going to call this the extrinsic curvature evolution equation. So this tells me how that extrinsic curvature is evolving along our redefined time vector. Okay? All of the differentials in this, as well as the Ricci tensor, depend only on the spatial metric, gamma AB. All right, so there's nothing out of the hypersurface in this. And so I have, in some sense, expressed the time derivative, how the extrinsic curvature is evolving in time, using only spatial quantities. Again, very convenient for the purposes of actually doing calculations. Okay. We need one more thing. Hey, I can erase this now because I've figured it out. One more thing. What other evolution equation do I need? What's left to figure out? Does the extrinsic curvature completely define the space-time geometry? The spatial metric. So I need to know how the spatial metric is evolving in time as well. That's actually a lot easier to solve for. So from the definition of the extrinsic curvature as minus 1/2 the lie derivative along the normal vector of gamma AB, I can substitute in the definition for the time vector TA and re-express this then as a lie derivative along the time vector now of gamma AB, turning things around a bit, is equal to minus 2 times alpha, the lapse, times KAB, the extrinsic curvature, plus the lie derivative along the shift vector of gamma AB. That follows trivially from the definition of the extrinsic curvature. When we do the same trick that we did before, we just substituted in to our lie derivative, the new time vector. Okay, and we're going to call this then the spatial metric evolution equation. And that's it, okay? We've got spatial metric evolution equation, extrinsic curvature equation. How many equations are they? Count them up. You remember, like 3 lectures ago, I told you the answer from the very beginning. And Eric asked, 12, that doesn't count. That doesn't add up. How many are there, Eric?
A to B goes 3, so 9 there.
Uh-huh.
I guess 3, 4 there.
Yeah, right, because they're purely spatial. And so even though our indices A and B go from 0 to 3,
Yeah.
the time components of all of these equations don't tell us anything. They're nil. So there's actually 12 equations here, supplemented by 4 constraint equations. And so my entire system of 3 plus 1 evolution amounts to 16 equations, all right? 12 of which are coupled evolution equations, 4 of which are constraints. The constraints I can solve at the initial conditions and be done with, because the evolution equations are guaranteed to maintain those constraints as I evolve forward in time. And that's it. Now, the cool thing about this is that if you think back to the full 4-dimensional version of the Einstein field equations, they're second-order differential equations, right? They involve second-time derivatives. They involve second derivatives of the metric, right? When you work out all the Christoffel symbols and connection coefficients. You look at this, this involves only first derivatives. So we've taken what was a second-order system and re-expressed it as a first-order system. And that's what we like to do in physics, because first-order ODEs are much easier to solve than second-order ODEs. And so this is a nice trick. This is a nice trick. Yes, technically there are more equations to solve. Technically there are more equations to solve than the original Einstein field equations, even counting the constraints. But for the price of that, we reduce the order of the ODE system. So that's a good deal. Any other questions? This is it. I actually managed to get them all up on the board at the same time in a somewhat clean way. What we've done so far is completely basis independent, right? We're working in abstract index notation, where I have not chosen a coordinate system. I've not chosen a set of basis vectors. To actually do calculation, especially numerically, we tend to have to choose a coordinate system. And so the next step is to take these equations and choose a basis and do so judiciously, because the proper and judicious choice of coordinate system and basis vectors will make our life a lot easier. Let me show you how we do that. All right. Goodbye, beautiful drawing. All right. The ADM equations. Arnovit, Thieser, and Meissner. And this Meissner is the M and MTW. Meissner, Horner, Lehman. Okay, so let's go ahead and now introduce some basis vectors. We're going to call this EA, lower parenthetical I, where the A is the components, right? 0 to 3, but the I is representing which basis vector am I talking about, right? Not its components. This is the notation that they use in Baumgarten-Shapiro, okay? Where I is equal to 1, 2, 3 for these different vectors, okay? Such that we're going to choose these basis vectors so that omega A times this basis vector dotted into the basis vector is 0, okay? So they're purely spatial. Purely spatial, all right? They reside entirely in sigma, our spatial hypersurface, okay? We can extend these vectors to subsequent neighboring hypersurfaces at later times by Lie dragging them along TA. This is how we get the basis vectors in the next subsequent time slice. Okay, and that's going to be Lie derivative along the time vector of my basis vectors is equal to 0. Somewhat like a geodesic equation. And that's how we're going to connect neighboring time slices. Okay. And just like before, we're going to want to do this in a way, and we do this because we want particles at rest to have the same spatial coordinates in neighboring hypersurfaces. And so we require that our basis vectors do this for that to be the case. Okay. So now, everyone's got this equation, right? I know I'm going to be writing it again, but here we go. Okay, we're also going to require that from the duality, that is, of the time vector with omega A, we can deduce the components of our time vector, okay? In fact, from these constraints and the duality here, we can deduce that the time vector is indeed A0, right? The one that we didn't specify up here. And more than that, we can figure out the components. 1, 0, 0, 0. Purely temporal. And now you see this choice of basis vectors makes this time vector exactly equivalent to the basis vector in the temporal direction. Convenient. Okay, so therefore, the Lie derivative along t, along the time and direction, reduces to just a partial derivative, okay? So along this time vector, this is going to be nothing but the partial derivative in t, in that direction, right? Where I've dropped the vector because this thing has only one component in the time direction. And if you recall from what we did in Thorne and Blandford, this is how we define basis vectors, as partial derivatives, geometrically speaking, right? So that works out, okay? Moving on, if we take our spatial basis vectors and dot them with omega A, what we get is -1 over the lapse, the normal vector dotted into our basis vectors, and that's got to be equal to 0 by requiring that, okay? So this implies then that the spatial components of the normal vector, that's actually the normal 1 form, but they've got to be equal to 0. As they should, right? We've said that this thing has got to be purely temporal. It points out of the hypersurface. Okay? I feel like this is the payoff, where everything all of a sudden starts to look simple again. And we drop a bunch of notational thingies. And it all starts to look like physics once more, because we've been doing a lot of geometry. Okay, so this also implies that all tensors with contravariant index 0. So upstairs zeros. For all of those, they vanish, okay? And that's because, for example, so normal vector, upstairs, contravariant, I'm going to make that a 0, right? I don't have to make it a 0 because this is purely temporal. So the normal vector dotted into the shift vector, that can only have temporal components. But the shift vector is purely spatial. And so that's got to be 0. Okay. And so all tensors with an upstairs index 0 are going to be 0 in this choice of coordinate system. This actually tells us what the shift vector is. So our shift vector is going to be equal to a 0 component and then just a spatial part. That's it. All right. Okay. Then from our definition of the time vector, alpha NA plus beta A, we can actually figure this out. We know, we already defined what the time vector was over there. We know what its components are, right? Up there. 1, 0, 0, 0. And we figured out what the components of this, the normal and the shift vector are. And so from this, well, we've determined what the spatial components of the normal one form are. And so for the normal vector, we get NA is equal to 1 over the laps minus 1 over the laps times BI. Just solving those equations. So now we have the components of the normal vector as well. Okay. All right. Furthermore, if we take the normal one form dotted into the normal vector, by definition, this has to be minus 1. And so that tells us what the components of the normal one form are. And that's minus alpha 0, 0, 0. All right. So now how about the spatial metric? So gamma AB, recall that our definition for the spatial metric was the full metric plus NA, NB, the normal vectors. So the spatial components of our spatial metric are just the spatial components of the 4 metric, because the spatial parts of these are 0. That's kind of convenient too, right? Now we're working with the 4 metric and just the spatial parts of it. So there's not any conversion between those components of these two tensors. Okay. Okay. And then from this requirement, all of these gamma A zeros must be equal to 0 because it's got an upstairs time index from this requirement. We can actually deduce the components of the 4 metric. And that's going to be, well, this is the inverse 4 metric. Gamma AB minus NA NB by definition. And that's going to be equal to minus alpha squared alpha, oh, that's a minus 2. So minus alpha to the minus 2, the laps, minus alpha to the minus 2 beta I, sorry, J, alpha to the minus 2 beta I up there, and then gamma IJ minus alpha to the minus 2 beta I beta J. So now we've got the full 4 metric and this basis, all right? We've got this portion of the 4 metric is the spatial 3 metric corrected by a term that depends on the laps and the shift vectors, and then some extra components in the time, where we know that gamma can't have any components up there. Okay. Another way of writing this is to write the interval, the line element, or ds squared is going to be equal to minus alpha squared dt plus gamma ij all times dx I plus beta I dt times the second term multiplied by dxj plus beta j dt.
That'd be a dt squared on the first term.
Of course it should be. Yeah. Okay. This is commonly referred to as the 3+1 metric. Okay. This is like a Pythagorean theorem for 4D, right? Like this tells us what the invariant interval is with this choice of basis in a 3+1 foliation of spacetime. Okay? It gives us the distance between events, and that distance must be invariant, whatever we do. Okay. With this choice of basis also, we can recast the Einstein field equations in terms completely dependent on their spatial components, which is nice. Okay, so let's start with the Hamiltonian constraint. I'm glad I didn't erase that at least, because here we go. So if you take a look at the Hamiltonian constraint over there, that's in four-dimensional form, but in this choice of basis, I'm going to cheat. Watch how I'm going to cheat. In this choice of basis, these temporal components got to be 0. So the Hamiltonian constraint just becomes that. Now it's going to take you longer to write it than me. Same deal with the momentum constraint. So this momentum constraint now, I can take all of these 4D indices on all of these equations, and I can turn it into purely spatial equations. All right, I'm going to have to rewrite this one. I'm going to rewrite it right here, because you got to bring in the spatial metric to change an index. Kij minus gamma ij times k is equal to 8 pi s I. And so that's what our momentum constraint then becomes. Yeah. So purely spatial equations now for my evolution in this basis. Okay. Let me write this here. And now we've got the evolution equation for the extrinsic curvature. And did you have a question, Eric?
Mike is having trouble saying past the computer.
I can't see any of that. But
Well, this was a bad idea then, wasn't it?
that's okay.
So this is a J. Can you see this at all?
I see the word momentum and then the screen.
Oh, super. I don't know how flexible this thing is.
That's
Is that better? Sorry about that. I got lazy. But that's dj kij minus gamma ij times k, the scalar, is equal to 8 pi s upstairs I. Okay. So then the evolution equation for the extrinsic curvature. Now I'm writing this as a purely partial derivative in time, because remember what we did with the lie derivative, which I've now erased. The lie derivative along the time vector is now just a partial derivative in time. Hey, this looks like a regular old evolution equation. That's going to be equal to minus d sub I d sub j, second spatial derivative of the laps, plus alpha times the spatial Ricci tensor minus 2 times k times k upstairs k downstairs j plus the scalar k, kij, close parentheses, minus 8 pi times the lapse, all times the spatial stress, Sij, minus 1/2 spatial metric gamma ij times scalar s minus rho, close parentheses, plus beta k, upstairs k, spatial derivative k, kij, plus spatial derivative in I, beta j, plus spatial derivative j, beta I. Oh, shucks. Wow. That's right. Those last two terms were not right. Sorry about that. Beta k, spatial derivative k of the extrinsic curvature ij plus extrinsic curvature ik, spatial derivative along j of beta upstairs k plus extrinsic curvature kj, spatial derivative along I of beta k. Can you see that? So that's a long one, but this is the evolution equation now for the extrinsic curvature, purely spatial. Okay, last one, evolution for the metric. This is shorter, and that's going to be, again, partial derivative in time gamma ij is equal to minus 2 times the lapse extrinsic curvature ij plus spatial derivative along I of beta j plus spatial derivative along j, beta I. That's it. That's it. So totally spatial components, right? We've eliminated all the time components now in this formalism. What else do we want to talk about here? We got 5 more minutes. So what we can do, I think the rest is just some formulaic stuff that you can look in the book about how to compute the Ricci tensor and the connection coefficients from this, but it follows immediately from our definition of the spatial metric. Eric, question?
Is it J on the last K?
The very last K?
Yeah.
Yeah, that's a J. KJ.
Okay.
Okay. Let's see, in 3 minutes, let's talk Schwarzschild metric. We got time. Still time on the board. Okay, so to spare myself from writing out the Schwarzschild metric, because that will take me 3 minutes, well, let's do it. We can do it. So ds squared minus 1 minus m over 2r over 1 plus m over 2r, all to the squared dt squared plus 1 plus m over 2r to the 4th, all times what looks like a flat metric, dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared, right? Cool. In this, just looking at our definitions for the spatial metric, which are no longer up there, but from this, we can get the lapse for the Schwarzschild metric, which is alpha is equal to, is there a minus sign there? I don't think so. 1 minus m over 2r over 1 plus m over 2r. The shift, beta of I is equal to 0. Spatial components of the shift are 0. Okay. The spatial metric, gamma ij, is going to be equal to 1 plus m over 2r to the 4th, all times diagonal matrix of 1 r squared sine squared theta d phi. No, not d phi. I don't need that in there. Right? And this metric takes the form where I could rewrite this as some factor times the flat metric eta ij, right? This is just the flat metric. And then this is some multiplicative factor. We would call this psi a conformal factor. And we'll use that later. Mike has read a lot of things about conformally flat metrics. Here it is, Mike. Well, at least this is the machinery that we will then use. Okay. And then finally, do I have room to write this here? No, I'll write it over here. And then that'll be it. We'll talk about anything else later. Finally, since this is completely independent of the shift vector, this has no dependence on the shift vector. Therefore, the extrinsic curvature is 0. Very convenient choice of coordinates in this case. All right. I'm done torturing you. Questions?
So the extrinsic curvature is 0. So does that mean that the Schwarzschild metric is flat?
No. No. So the metric itself is still not flat, right? The metric itself is not flat, but the extrinsic curvature in this choice of coordinates is 0. That tells us how it evolves.
Okay.
Right? That gives us sort of boundary conditions for how the metric is then going to evolve in time, right? Because metric evolution equation has the extrinsic curvature in it. So for this choice of coordinates, that term is 0. The metric evolution depends only on spatial derivatives of the shift vector, which is also 0. But it doesn't mean that the space-time is flat. It means that the evolution is very simple.
Okay.
It means that solving these equations in this case is pretty straightforward. Which is why Schwarzschild metrics are always a fun favorite. Other questions? There's still gravity. The black hole will still not quite suck you in, pull you in.
But it's steady state.
Yeah, that's right. That's right. Right? Because there's no time derivatives. We mentioned that before about the Schwarzschild metric and the fact that that gives rise to a killing vector, right? There's no time components in here, right? There's no time components, so it's steady state. Right? And so both of those equations, the evolution equation for the extrinsic curvature will also be 0. Partial T Kij is 0. That's 0. Easy peasy. Steady state. Thank you. All right. For next week, read chapter 3. And again, no class on Tuesday. I'll be out of town, so we'll pick up on Thursday. But read chapter 3 by Thursday, and then we'll get back to it.